before the lecture starts, no.
Online? Online participants we cannot, yeah, we just have to take photos. So
one announcement. I think before the lecture started, we had mailed you that there will be a poster session at the end of this, all the lecture sessions. So you are to prepare a poster on your own work or whatever based on one of the topics that you have learned here. Okay, you are free to choose the topic that you want to present, but it has to be either your own work in Spintronics or something that you have learned here. Okay, and poster dimensions and all, better make a slide and display the poster dimensions. So there is no problem. Okay, we will help you print out. You just need to submit it to us by the deadline. We will get the printout of it. Okay, so we will need to we can probably create a form where they can upload or some folder where they can submit posters. So it's easy. Otherwise they will come with sometimes it's difficult. So deadline will keep up Friday. Saturday we will have this poster in the okay. So Friday sometime we'll give the time also. What is the deadline? Please prepare the poster and upload in the drive or some link will be shared with all of you. Upload there and we will print it out on Saturday morning and we will display it. Somewhere in this lobby we will put a poster. Okay. So if there are any confusions, ask us. We will also provide you the dimensions and all that. Okay. Today towards the end, make another announcement and on the WhatsApp group also make the same announcement. You
okay.
want to add something?
No.
This is what I am.
Yeah, it's fine. Yes. So Friday they have exam. I
Friday,
hope they remember. Yeah.
Yeah. Friday you also have exam. So Friday you also need to submit the poster. Saturday we will have the poster.
Hello.
Okay. So I think we can begin with the sessions. Yeah.
Okay. Thank you. Yeah. See you. Okay, good morning. So let's start. So far until now you heard about how do we use Spintronic principles for reading information in hard disk drives. So from today onwards we will be learning about MRAM, how do we write information, how do we store information, what are the parameters that determine the readability of MRAM and things like that. Okay. So today we will focus on the writing methods, how do we write information. Okay. So you might think that magnetic random access memory is very new, okay, but it is one of the oldest random access memory. Okay. Even before the DRAMs, SRAMs were introduced, the computers used magnetic memory. Okay. So DRAMs and MRAMs came in 1960s and later. okay, whereas in 1950s computers used magnetic memory. So, it is called magnetic core memory. So, these are tiny pieces of magnets. So, the information is stored here, and you can see copper wires going through. So, these are like toroids. So, it is like a circle with a hole, it is a kind of ring. Then you send wires. So, you use these wires to write and read information. Okay. But after, I mean, these things are made using hand, So, like people use people make sweaters. So, it is like making sweater. So, people use the toroidal rings and copper wires and make these memories using hand. Okay. So, kind of handicraft memory. But once we could make SRAM and DRAM by lithography, mass manufacturable, then this memory died. Okay. Now, after almost 50 years, now the magnetic random access memory is coming back. Okay. Like old Hindi movies of 1980s, the father gets killed by villain, then son comes out to take revenge, right. So, now the MRAM is coming up, probably to replace some of these villains. So, this is how the MRAM will look like. So, you have a transistor and you have this magnetic tunnel junction. Okay. So, in magnetism you will come across the words TMR and MTJ quite often. So, when you encounter the word TMR, it refers to tunneling magnetoresistance. So, basically this represents a phenomenon, right, physical phenomenon, whereas MTJ refers to magnetic tunnel junction. So, it represents a device. Okay. So, TMR represents a phenomenon, magnetic tunnel junction represents a device, and people of two different industries use different terminology. So, people in the hard disk industry, they use TMR sensors. Okay. So, they call the sensors based on the phenomenon, because we have been using AMR sensor, GMR sensor. So, it is quite likely that they continued the tradition of TMR sensors for reading information. So, they call the sensor based on the phenomenon, whereas the MRAM community uses the word MTJ to represent the device that stores the information. So, here this MTJ can have high resistance or low resistance depending on the parallel or anti-parallel nature of magnetization in the two layers. So, they represent states 1 and 0. Okay. We are storing digital information. So, bits 0 and 1 are represented by having parallel magnetization or anti-parallel magnetization. So, like in the TMR sensor that we learnt, so we have one fixed layer. Okay. So, this magnetization is always fixed to one direction and the free layer direction is different. Okay. So, as I mentioned before, the fixed layer has many different terminologies. So, some people call it hard layer, some people call it a reference layer, fixed layer, pinned layer. So, all these terminologies mean the same thing. The layer whose magnetization does not change is called any of these layers. Okay. Then the magnetization of the second layer is varied as per requirement. So, today we are going to learn about writing, right. What do we mean by writing? What do we mean by writing? Pardon? Storing information, that is storing. Writing, I am talking about writing. So, you take your notebook, write using pen, right, that is writing. Storing means after you write using the pen, the information is stored. Okay. So, I am talking about writing. What do we mean by writing? Yeah. Okay, we have some format. What do I mean by writing? I have some information. What do I mean by writing? Recording. What does that mean?
So in terms of magnetization,
Mm-hmm.
like we are magnetizing the material and that's how we are applying the magnetic field.
Mm-hmm.
So that's what we can say reference to this.
Okay, so we do some action to make these layers parallel or anti-parallel. Okay. So, if we apply magnetic field or do some other action to keep the magnetization of the two layers parallel, that is writing 0. Okay. So, if we take some action out of which these two magnetizations are anti-parallel, we are writing 1. So, writing 1 or 0 is magnetizing the free layer in one direction or the other direction, that is basically the writing. Okay. So, in magnetic recording I told you, right, we have an electromagnet. So, we generate magnetic field. So, these electromagnets generate a magnetic field which keep the magnetization in one direction or the other direction, that is the writing. Okay. So, in a similar sense, in magnetic random access memory, writing 0 means keeping the free layer magnetization parallel to the reference layer magnetization, that is the writing 0. So, if you want to write 1, you switch the magnetization of the free layer to be anti-parallel to the fixed layer, that is writing 1. Okay, so, here if you notice, we have a transistor at the bottom, then MTJ is at the top. Okay. So, if you remember the first day of our lecture, I gave you the DRAM circuit, and in the DRAM the capacitor was somewhere here. So, this capacitor was used to store 0 and 1. So, in DRAM the capacitor is at the bottom of the transistor, but in MRAM you will notice that the MTJ is at the top of the transistor. Why? Why is it so? Okay, so, if you take the DRAM of a semiconductor chip, the capacitor of a DRAM, what is this capacitor made of? Pardon? Dielectric. Okay. Yeah, you can say. So, this dielectric is part of the semiconductor manufacturing process. Okay. So, in semiconductor manufacturing process, you have silicon, you may dope with something, phosphorus or boron, and you may have some dielectrics. So, these are all part of the semiconductor manufacturing process, okay. So, which have been there for many years, almost for 50 years this process has been established. Okay. Suppose now you suddenly want to move to MRAM technology. So, in MRAM technology you have a copper wire here, then you have so many like antiferromagnetic materials, ferromagnetic materials. So, you are introducing so many new materials, okay. And later you will learn that after you make the MTJ, you will also do annealing at around 350 degrees Celsius and so on. Okay. Imagine you have this MTJ somewhere here and you do all these things, what will happen? What will happen? So, all these cobalt, manganese, they will go into the transistor element. So, you know the semiconductor chip is supposed to be very clean, you cannot have, it is a semiconductor material, right. So, you are controlling the doping very precisely. Okay. So, if you have all these elements and do annealing at 350 degree Celsius, all these materials will go inside your semiconductor chip and your transistor won't function. Okay. So, we want to keep the semiconductor technology immune to everything else we do for MRAM. Okay. So, we do not want these things to be affected by whatever we do at the top. Okay. That is why we keep all the semiconductor related parts at the bottom. Then we have some copper, some metallic layers. Then we do all these things at the back end. So, it is called back end of the line processing, something like that. Okay. So, we do all the other operations like depositing the layers of MTJ, all those things we do after we finish all the transistor part. Okay. So, if you look at a memory array, it will look something like this, right. So, memory array you have word line and a bit line, and if you want to address some particular memory, so you send current through one row and another column. So, this particular thing will address this memory and things like that. So, MRAM also is very similar, except that now here we have that transistor and the MTJ, this thing is here. Okay. So, that is how we have MRAM. So, if you look at this picture, you can see that this whole thing is related to the transistor part. I am not very good in this semiconductor electronics, but these are all things related to the transistor part. Then on top we have this. Okay. So, these are the MTJs, magnetic tunnel junction. So, if I zoom in, it will look something like this. So, we may have the MGO here, free layer somewhere here, and reference layer, all those things. Okay. So, this is the magnetic tunnel junction that stores the information. Okay. So, as we learned before, I told you that I will keep repeating this triangle until the end of this course. So, whether you make a memory, I mean we are talking about some non-volatile memory or storage. So, when we talk about a non-volatile memory or storage, we should have some ability to store the information, retain the information, some ability to read the information, some ways to write the information. So, all these three criteria must be met. Okay. So, for example, if there is a water bucket, right, you write with your finger, you can write information, but water won't store information. So, writing alone is not enough, or if storing alone is not enough, you should be able to read also. All these three criteria must be met when you design a memory or storage element. Okay. So, today we will focus on the ways to write information. Okay. So, like the semiconductor technology progressed following the Moore's law, the capacity of the chips doubled, I mean the number of transistors in a die kept doubling every year. Then somewhere in 2000 people realized that we cannot continue to grow in the Moore's law method, we have to rely on other alternative technologies. So, different communities started working on different topics. So, we have ferroelectric RAM, phase change RAM, STT, MRAM, field switching MRAM and things like that. Okay. So, ferroelectric random access materials use the materials like PGT kind of dielectric material. Phase change RAM uses the materials used in CD or DVD. Okay. So, these materials are amorphous. When you heat them and cool them, rapidly they will become amorphous. When you heat them and cool them slowly, they will be crystalline. Okay. So, this PCRAM has a high resistance in the amorphous phase and low resistance in the crystalline phase. Okay. So, you can store 1 and 0 using PCRAM. So, various communities. So, people working on different materials, they were looking at alternative memories. Okay. So, the MRAM that we are going to learn today is competing with so many other candidates. For example, if you look at SRAM, SRAM occupies very large area. I will later explain what is F square, and SRAM also has a leak current. For example, SRAM is like a bucket where you keep adding water and water also leaks. Okay. So, if you want to store information in SRAM, you have to keep supplying energy. Okay. So, the energy required to keep the information in SRAM is quite high, and okay. So, every memory technology has some advantage or disadvantage. So, in that sense STT-MRAM has certain advantage and it has been implemented as a niche memory replacing something called E-flash. So, E-flash is some memory in your say digital watch or mobile phones where some programs are stored. Okay. So, when you start your phone or your watch, the program will be taken from this E-flash and run, things like that. Okay. So, there is some small memory different from SRAM or MRAM. This is another type of memory, non-volatile memory. Okay. So, this is where MRAM is currently being used, and we are looking at some other technology which may probably replace SRAM. These are the research work that is happening, and SRAM and DRAM are volatile memory. That means, if you switch off the power, they will lose the data, whereas MRAM is non-volatile. Okay, it will retain the power even if you switch off the power. Okay, so, there are some advantages because of which the industry have invested money and they are developing MRAMs, and they have achieved some success and they are in the path of making more products using MRAM. Okay, so, you can classify MRAMs into different types based on the writing methods or the way in which you store information and things like that. Okay. So, people give names like toggle MRAM to represent MRAM which uses certain way of writing. So, if you use a spin transfer torque for writing information, we have STT-MRAM and things like that. Okay. So, depending on how do we write information or how do we store information, there are many names for MRAM. Today we will focus more on the writing methods. Okay. So, at first we will learn about magnetic field assisted MRAM, then we will move to spin transfer torque MRAM. So, this is like chronologically, this was the early method of writing MRAM, and this is reasonably new. So, people have started studying writing information based on spin transfer torque somewhere around 2007 and later. Okay. So, this is even before 2000. You can say before 2005 or something like this. So, we will learn about some of the old technologies, then we will move to new technology and newer technologies. Okay, so people often use the word switching to represent writing. Because as I mentioned, the reference layer is always in one direction. So, you switch the magnetization to be anti-parallel or parallel, thereby you write 1 or 0, right. So, basically you are switching the magnetization. So, that is why people use the word switching. So, switching basically means writing information. So, you write 1 or 0 by switching the magnetization direction. Okay. So, let us start with the magnetic field assisted switching or writing mechanism. So, in this case we are using magnetic field. So, if you remember, in magnetic recording we are using magnetic field to write the information. So, we magnetize the materials to be pointing up or down or to have magnetization left or right. Okay. So, we write bits by using electromagnet, which generates a magnetic field. So, in a similar way, in the field assisted MRAM, again we are using a magnetic field to write information. Okay. So, in magnetic recording we had a coil, then we have a ferromagnetic core. So, we use this core magnetic field to write information. So, if you remember the lecture on magnetism, I taught you 3 ways of producing magnetic field. Okay. So, in the first case I told you if you send a current through a wire you will produce magnetic field, not something like this. Then second one was solenoid, third one was solenoid with a ferromagnetic core. Okay. So, the third one is the one we use for magnetic recording. Okay. But for this field assisted MRAM, we are going to rely on this method. You have a wire, okay, you send current through the wire, then you produce a magnetic field. So, I told you that you can use your right hand to determine the direction. So, if this is the direction of your current, magnetic field is following the direction of your other 4 fingers. Okay. So, in this MRAM, a magnetic field is produced by current carrying wires, and we are using this magnetic field to switch the magnetization. Okay. So, look at the emphasis, it is not current carrying wire, I am using current carrying wires. Okay. So, there are more than one wires. Okay. So, there will be at least 2 wires. Okay. So, we have 2 wires and we produce 2 orthogonal magnetic fields. So, that means let us say one wire is coming towards you, this wire is producing magnetic field in this direction, say your anti-clockwise direction. Then we have another wire in the orthogonal direction. So, this wire is producing a magnetic field around this direction, okay, which is coming towards you going this way. Okay. So, we are producing 2 orthogonal fields to switch a particular MRAM. So, basically a particular MTJ element, magnetic tunnel junction. Okay. So, we will be sending current through the read line and bit line. So, if you remember the memory array I showed you a few minutes ago. So, we had a memory cell here. So, this memory cell is accessed by a certain word line, then certain bit line. Okay. So, in the case of this particular MRAM, we are sending current through 2 wires, one wire which belongs to the read line, another wire which belongs to the write line. Okay. So, we are using 2 wires to produce 2 magnetic fields. So, in this picture you can see we are sending current through one wire, it produces certain magnetic field. We are also sending current through another wire which produces another field. So, these two fields are orthogonal to each other, 90° with respect to each other. Okay, so, now I will show a brief animation to show how it works. Okay, so, in this picture you see two wires, one blue wire going this way, another blue wire going this way. So, the MTJ is somewhere here. Okay, inside this there is an MTJ. So, you cannot see what is happening here. So, let me bring it out. Okay, MTJ has come out now. So, you have two layers, one magnetization is fixed, another one is free. Okay, so, when you send current through only one wire, you produce certain magnetic field. So, that magnetic field has rotated the magnetization direction from being parallel to somewhere in this direction. Okay. Now, we send current through another wire. Okay, so, this current was making the magnetization to go in some other direction, but it could not switch. Okay. It did not become anti-parallel. Okay. So, we started with parallel magnetization. So, switching happens means it become anti-parallel. So, we are writing 1. Okay. So, by sending current through this wire or this wire alone, we could not switch the magnetization. We are only temporarily rotating the magnetization from one direction to the other, but after you remove the current, it goes back to the initial state. Okay. But when you apply both current, I mean current through both the wires, you can see the magnetization has reversed. Okay. So, the two magnetic field act together to switch the magnetization of the free layer. Okay. We use many terminologies. So, for this layer people use free layer, storage layer and so on. Okay. Okay, now watch again. One current does not change the final state. So, only by sending current through two wires we can switch the magnetization of a particular MTJ.
Storage device is in between the two wires.
Somewhere, I mean, now let us say you are viewing from the top. Okay, so, this is one wire, then below this you have this MTJ, then this wire is at the bottom of. So, it is like top electrode, the other one is like bottom electrode, you can say.
How this bottom layer affecting the storage layer, because there will be a fixed layer also in between?
Yeah, this field is not enough to switch the fixed layer magnetization. Fixed layer has a, fixed layer is pinned with a antiferromagnetic material. So, you cannot change this easily.
Magnitude is very low.
Yeah, the field is very low. Yes. Okay, the title of this slide is selective switching. So, what is the meaning of selective switching? So, why I use this word here? No, current direction, yes, of course, but why do I use the word selective switching? Pardon? You speak up.
So we are just the magnetization of the upper layer.
No, that one is not the reason why I use this.
In the array of many MTJs, maybe we can select one particular which we want.
Yeah,
and
exactly.
leave the others.
Yes. So you have an array of I mean you have write line, bit line, right. So, let us say we call this write line and we call these bit lines. Okay. Let us say you want to write information on the MTJ here. Okay. This MTJ is the one you want to target. Okay. So, you want to make this say from 0 to 1. Okay. So, you want to write information 1 here. Okay. So, what you do, you send current through this wire B 2, then you send current through this wire W 3. Okay. So, this whole wire B 2 produces certain magnetic field. Okay. So, throughout this wire you will see the magnetic field going like this. Okay. So, if this magnetic field is strong, it will write all the MTJs. Okay. So, similarly, you send current through this wire, this will produce magnetic field throughout the length of this wire. So, if this magnetic field is strong, again it will write all the MTJs. Okay. So, what we are doing is we are sending a current lower than certain critical current, that any MTJ along this wire do not switch. Okay. The current in the word line or current in the bit line, sorry, is lower than critical current. Okay. So, that the magnetic field produced by this wire does not switch any other MRAM. Okay. Only the MRAM which is under the intersection of this IW and IB will switch. Okay. So, by choosing the two wires, we can selectively switch the MRAM cell we want to switch. Okay. So, that is the reason the word selective switching is used here. Okay. Yeah. Yes, the current carrying wires are traveling across the array. So, it is like yes. So, you have one wire going this way. So, one wire covers many MTJ. So, one wire in the right line or one wire in the bit line, they cover many MTJs. But the current we send is not enough to switch any MTJ. Okay. Current in any wire is not enough to switch any MTJ, but only when you have the two orthogonal fields, two orthogonal magnetic fields, you can switch the MTJ. Okay. So, this is the mechanism. So, what happens? What is the physics behind it? So, we will learn that now in the next few slides. Let us say this is the free layer of the MTJ. Okay. So, you know that because of shape anisotropy, we have one easy direction, we have a hard direction. Okay. This is the top view of the free layer, it is like this. The side view is something like this. Okay. So, in the absence of anything, the magnetization is pointing towards left. Okay, let us do the hysteresis loop of this particular piece alone. Let us forget about this one. Let us say we have deposited a free layer and let us do a hysteresis loop. Okay. So, we apply magnetic field along the easy direction. Okay. Sweep the magnetic field. So, we will get a hysteresis loop. It will look something like this. going back. So, we will have the hysteresis loop looking like this. Okay, so, the coercivity is around say let us say 47 Oster. Okay, so, this is a normal hysteresis loop. Normal hysteresis loop, we just apply some magnetic field, we sweep some say minus 75 to plus 75, then we get this hysteresis loop with a coercivity of 47 Oster. So, this is the experiment number 1. Sweep H and measure, let us say magnetization or MR, does not matter. Okay. The second experiment, what we are going to do is we are going to apply an external magnetic field along the hard direction. Okay. So, we call it H hard. Okay. We apply some magnetic field along the hard direction. So, let us call it with a suffix H hard. Okay. So, in the presence of this hard magnetic field, now we do the second experiment. Okay. Now, in the earlier experiment the hard field was 0. Now, this hard magnetic field has some finite value. So, we sweep magnetic field again, we measure the MR. So, for example, if you look at this image, this curve was measured when the external magnetic field. So, in this particular picture, for example, external magnetic field will be going towards the board. Okay. In the side view, this is the easy direction. So, you are applying transverse to the easy direction. In the top view, H hard is along this direction, H easy is along this or this direction. Top view is like this. In the side view, H easy is either along here or there, we are sweeping, and the hard magnetic field is always in one direction. Okay. These two are orthogonal direction. Okay. So, let us take this curve 40 Oster, we apply a magnetic field in the hard direction and its magnitude is 40 Oster. We are not sweeping this. Okay. This is fixed value, one value of H hard. We are only sweeping the magnetization in the easy direction, like what we normally do for measuring hysteresis loop. So, in this case, let me use another color. In this case, when I measure hysteresis loop, it looks like this. So, we see a hysteresis loop which looks something like this. So, what is the major difference you see now? Yeah. I mean, not all questions are tricky, some questions are very simple. So, feel free to answer without being scared. Okay, it is very obvious, right? Coercivity has reduced. Okay. So, when you measure the hysteresis loop of a sample with only one magnetic field sweeping, you have coercivity of 47 Oersted, but when you have magnetic field in the easy direction and hard direction, in the presence of two magnetic field, now the coercivity has reduced to something like 20 Oersted. Okay. So, that is what you see here. So, this is what we do in the selective switching. Okay. So, we are applying two orthogonal field, right. So, if you remember, we have a bit line, digit line, both of them are generating a magnetic field. Okay. So, we are using two magnetic fields orthogonal to each other, which means the coercivity of the free layer here will be much lower than the coercivity of the all the other MRAM cells. So, what causes this reduction of coercivity? Okay, so, we learned that two magnetic fields produce lower coercivity. So, what causes that? So, that is explained in this picture. So, we will come back to the energy landscape again. So, when we talk about energy landscape, we are plotting energy as a function of the magnetization angle. Okay. So, for example, 0 means magnetization is pointing in one direction, pi or 180 means magnetization has switched by an angle of 180 degree. Okay. So, these two are the two easy directions. Okay. So, in the absence of any magnetic field, so we learnt that the Stoner-Wohlforth particles will have two energy minima, right. So, magnetization pointing in one of the two easy directions. And we also learned that these two states are separated by an energy barrier E b. So, do anyone remember what is the value of E b? So, what is this E b equal to? K u v. Okay. So, K u is the anisotropy of the material, V is the volume of the grain. So, in this case we are doing lithography. So, we can say the volume of the island. So, here volume is actually the volume of the free layer. Okay. So, the free layer and the reference layer are separate magnetic entities. So, here we are talking about the volume of the free layer. Okay. So, the free layer has material has certain anisotropy constant, you multiply the volume of the free layer. So, let us say the diameter of this is like 60 nanometer, then let us say this layer has a thickness of 3 nanometer. So, you can calculate the volume of this particular cylinder. So, that volume multiplied by the K u is the E b. Okay. So, when you apply no magnetic field, this is the energy landscape. Let us say this is your free layer viewed from top. Let us say the magnetization is pointing in this direction. Cross section, okay, I am not drawing cylinder, I am drawing a cuboid. Okay. So, side view is like this. Okay, the magnetization of this particular the free layer is pointing like this. So, right now it is okay, let me change the direction. To be consistent with that picture, let me use this. Okay. So, this is your initial state. So, we are here. Now, let us say we apply a magnetic field. Okay. So, this is the easy direction. This is a hard direction. Let us say we apply a magnetic field along the easy direction, the opposite to its magnetization. So, in the absence of magnetic field, this was very low energy, but once you apply an opposite magnetic field, the energy landscape changes like this. So, now H E Z is not 0. So, it has some particular value. So, it changes the landscape like this. Okay. So, you can notice that this state is becoming more unstable. Okay. But this field is not enough to switch, totally switch. So, in magnetic recording, we apply this magnetic field value very large, so that this goes all the way here. So, our EZ field was even higher. So, the magnetization cannot stay here, it will switch to the other direction. Okay, that is what we did in magnetic recording, but here we are not doing that. So, here we are applying a field in the EZ direction, not high enough. Okay. So, it just enough to reduce this energy barrier. So, you see now the energy barrier is reduced to a lower value. So, here the energy barrier is so high. So, when you apply the certain magnetic field, now the energy barrier is reduced. Okay, this is one scenario. We are applying magnetic field only along the EZ direction. Now, let us do another experiment. I use another color. Now, we are applying magnetic field in the hard direction. Only in the hard direction, okay? No field in the EZ direction. So, if I apply magnetic field only in the hard direction, that changes the energy barrier landscape like this. Okay. So, again applying magnetic field in the hard direction has reduced the energy barrier to certain height, lower height. Okay. So, you see this height is lower than this. Now, if you apply both together, okay, so there is a EZ direction magnetic field and hard direction magnetic field. So, what happens? The hard direction reduces this energy barrier height, and the application of the magnetic field in the EZ direction changes the energy landscape further. So, these two together will bring out this scenario, where this is no longer stable, this is the stable. So, the magnetization will switch to the opposite direction. Okay, so, why the applied magnetic field changes the energy barrier? So, you can understand based on these equations, okay, but I do not spend time on equation, but this is the concept. Okay. So, by sending current through two orthogonal wires, you change the energy barrier landscape from this to this. So, that particular cell switches magnetization. All the other cells, for example, the MRAM cells in the EZ direction, I mean we are sending current through two wires, right. So, all the MRAM cells in this particular are having energy barrier like this, they do not switch, and all the other cells in this particular, for example, this MRAM, they undergo energy landscapes change like this, they also do not switch. Only this particular MRAM, which is at the intersection, have this energy landscape. So, only this can switch. Okay, so, that is the field assisted MRAM. So, people can do, so what people do is like when they create memory array, they send certain current through the digit line, certain current through the bit line. So, bit line, word line, read. So, you can send current through two orthogonal wires. So, when this current is low, nothing happens, or when this current is low also nothing happen. But if these two values are of certain magnitude, for example, this digit line has certain value and bit line has certain value, this particular MRAM will switch. Okay. So, any current higher than this will definitely make the MRAM switch, but if you apply a digit current lower than this, it will not switch. Okay. So, only in this region the MRAMs can switch. So, these are the operating regions. Yes. So, the two wires in the orthogonal direction, they are providing the easy field and hard field. Yes, correct. Okay. So, I gave you one explanation of how this whole thing works. There is also another explanation, but I think we can skip this today. Okay. So, this I told you that this switching technique was used until say 2006, but after this people dropped this and moved on to spin transfer torque MRAM because of certain limitations. Okay. So, the first limitation is that this technology is not scalable. Okay. So, what do you mean by scalable? We have used the word scaling before. Anyone remembers what is scaling? Yeah. So, reducing the bit size, reducing the bit width, okay, bit length or bit width. So, scaling is basically making, I mean in semiconductor or magnetic recording technology, when we talk about scaling, we are talking about reducing the area occupied by 1 bit. Okay. The area required to store 1 bit. So, we want to keep reducing, we want to store more bits in a given area. So, when we are talking about scaling, we are talking about reducing the area required for storing 1 bit of information. So, in semiconductor technology, we talk about the area required in terms of something called f square. Okay. Let us say you have some lithography technology. So, with that lithography technology, you can resolve lines with a resolution, let us say f nanometer. Let us say your lithography technology can achieve 5 nanometer resolution. Okay. So, we call this as f. So, if you remember, historically this used to be this semiconductor technology used to have techniques like 180 nanometer node, 90 nanometer node, 45 nanometer and things like that. Okay. So, now we are in the 7 nanometer node, 5 nanometer node like that. Okay. So, basically these numbers represent the f, which is the minimum feature size you can achieve using lithography, and we express the area occupied by a particular memory cell based on that number. Okay. So, if f is 7 nanometer for example, so f square is 49. So, this whole thing will be 980 nanometer square, okay, something like that. So, if the minimum feature size is 7 nanometer, 20 f square will be 980 nanometer square. So, people do not use 980 nanometer square, but they will use this kind of terminology. Okay, so the first problem is that this magnetic field switching technology is not scalable. So, you can see from this picture, let us say 20 years ago we were in 1000 nanometer dot. So, your cylinder had a diameter of let us say 1000 nanometer, which will occupy a large area, right. So, you want to move towards say 100 nanometer or 10 nanometer. So, the progress is along this direction. So, you have bigger bit, then you want to make smaller and smaller bits. So, this is the direction of progress. Okay. So, in this image, so the direction of progress is along this line. Okay. So, we are going from 1000 to 100 to 10. This is the direction in which we want to progress. Okay. So, if you look at the current, we need to write information. So, at 1000 nanometer we have like say around 8000 microampere is needed, but if you make the bits smaller, you need more current, say 12,000. If you make the bits even smaller, you need even more current. Okay. So, the current required to write information keeps going up. Okay. So, this is a problem. So, you want to make the devices smaller, but as you make devices smaller, the current you need to write information gets larger and larger. Okay. So, this is the problem. So, that is why it is not scalable. Okay, that is what I mentioned here. And this current, this large current also cannot be supported by transistors. So, as you go from say 45 nanometer technology to say 28 nanometer technology, the current delivered by say a transistor in 45 nanometer will be higher. The current delivered by a transistor in 28 nanometer will be lower. Okay. So, as you go towards better and better technology, the current delivered by transistors is going lower, but current we need for writing information is getting higher and higher. So, we are in a problem. Okay. So, this is not useful. Okay. This is a problem. So, because of this problem, this technology became obsolete. Now, nobody is using this technology. Okay. Okay, let us do some questions now. Wait a minute. Okay, the title does not match. This is the actual question. Okay. The title does not match the question. Okay, most of you are right. So, we preferably we want the MRAM pre-layer to reverse by Stoner-Wohlforth reversal mechanism. So, all the switching concepts I described, the energy landscape, all of them follow the Stoner-Wohlforth reversal mechanism. Okay, so, the correct answer is this. Next question. Okay. Okay, this question works. This on. It's a bit hot. Maybe switch that on. This one is off. Okay, the total switching current required to switch an MRAM layer of 1000 nanometer was 10 milliampere. So, in the case of field assisted MRAM, if you shrink the MRAM size, the current is supposed to increase. Okay. That is the problem that we learnt. So, it will not be 10 milliampere, it will be a larger value. Okay. So, the correct answer is supposed to be 4. Okay. Majority of you are right, but many of you are wrong also. Okay. So, I just described that the problem of field assisted MRAM is if you shrink the MRAM cell size, the current required gets larger. So, instead of 10 milliampere, it should be a larger value. So, the only larger value in this question is 50 milliampere. So, 4 is the correct answer. Okay, this is not working. Okay, this one we have seen. Okay. Okay, so we have almost finished everything. Is it time for break? Okay. Yeah, so we go for a break, then come back by 11:30. Okay, so let us move on to the next topic, which is the STT MRAM, where STT stands for spin transfer torque MRAM. Okay. So, this is another technique to write information. So, unlike the previous case of a magnetic field MRAM, where we send current through two wires to switch one particular MRAM, in the case of spin transfer torque MRAM, we send current directly through the magnetic tunnel junction to write the information. Okay, so, the magnetization of this particular free layer will reverse by something called a spin transfer torque mechanism. Okay. So, we will learn what is spin transfer torque, how does it work in the next few minutes. So, before we go on to understand what is STT MRAM and so on, here I want to say why STT MRAM is better than the magnetic field based MRAM. So, first of all, you look at the area occupied by the field based MRAM. So, it is 20 to 30 f square. STT MRAM is only 6 f square. So, as I mentioned, so let us say if f is 7 nanometer, let us make it 100 nanometer. Okay. Easy to calculate. So, if f is 100 nanometer, so 20 f square will be like so 200,000 nanometer square, whereas this will be like only 60,000 nanometer square. Okay, so, the area occupied by STT MRAM is smaller, that is one thing that you can see. Secondly, you look at the device, right. This looks quite simple. So, you have a bit line, the current flows through, quite simple lithography, but if you look at this one, it looks very complicated. Okay. So, the number of lithography steps or fabrication steps will be many more in the case of the magnetic field based MRAM, whereas it is quite lower in STT MRAM. Okay, so, these two are some advantages of STT MRAM over the field based MRAM, but the most important advantage is in the scalability. Okay, so, I told you that when we reduce the transistor size or the MTJ size, if current increases, this is a problem we do not want. Okay, so, we want the current to be reduced as we go towards smaller and smaller sizes, which you see here. Okay. So, in the case of STT MRAM, for example, the current that you need to write information goes down as you go towards smaller sizes. Okay. So, this indicates that this STT MRAM technology is scalable. So, when you make the MTJ smaller, the transistors also will be smaller. So, the transistors will be generating lower current. So, all this are possible. Okay. So, these are some of the advantages of STT MRAM. Okay, so, to understand how the STT MRAM functions, so we need to revise some of the concepts that we learnt. Okay, so, in your undergrad or school days, you would have studied angular momentum. So, angular momentum can come from various sources. So, if you take a spinning fidget spinner, for example, here this intrinsic angular momentum, some cases you can have extrinsic angular momentum and so on. Okay. And you can transfer angular momentum from one object to other object. So, last time I asked some of you to rotate the fidget spinner and try to change the direction. So, you will feel some force on you. Okay. So, I will pass around, you can play during my lecture. Okay. So, I just rotate, hold it in your finger, then try to change the angle, you will feel some force on you. Okay. That is because the fidget spinner has some angular momentum, and when you change the direction, you are changing the angular momentum. That means, there is a torque, and that torque will act on your finger. So, you will see that as a kind of force. Okay. So, angular momentum can be transferred. Okay. So, this also something that you need to remember. Okay. So, I will play a video. Okay, watch this video.
Conserved angular momentum. So I'm going to lift my feet off the ground, try not spinning. My assistant's going to come and spin this for me.
Okay, so now the angular momentum is either that direction or this direction.
So I have some angular momentum. Now when I rotate it, start to spin. If I want to stop myself, stop. If I go the other way, I spin back around.
Okay, so he is changing the angular momentum of the wheel, and because of that there is a torque acting on him, which makes him to go around. Okay. So, this is the property that we exploit in the case of spin transfer torque MRAM. Okay. So, to understand the concept of spin transfer torque MRAM, we need to understand two basic terminology. First terminology is spin polarization, then the second terminology is angular momentum transfer. Okay. So, yesterday when we learnt about the giant magnetoresistance concept, I introduced the modes. Modes two current model. So, we learnt that current flows in two different channel, one for upspin, one for downspin. This is something that we learnt, and we learnt that the, let us say if the magnetization is in this direction, the spin up electrons which have magnetic moment in the same direction, they scattered less. Okay. On the other hand, the spin down electrons which have magnetic moment opposite direction to the direction of magnetization, they get scattered more. Okay, so based on this, we used these terminologies like alpha. I don't know why it's not working. Okay, so if you remember, we used, I don't know why it's not working. Okay. It's not writing.
You can see on some other slides if it's
Mm-hmm. Now it won't work. You have to go to slideshow. Okay, now it's working. Let's go to. Okay. Okay, so we learnt Mott's two current model, and we learnt that the minority electrons whose magnetic moment is anti-parallel to the direction of magnetization, they get scattered. Okay, so the probability of them going through is less, they get scattered. Okay, so this is what we learnt through the alpha. Okay, in ferromagnetic materials, alpha is more than 1, which means the minority electrons get scattered. Okay, so this is something that we learned. Let us say you have a ferromagnetic layer and a non-magnetic layer, and you send electrons from one particular direction. So, this spin up electrons will go through, and the spin down electrons will get scattered. Okay, scattered back. So, they may accumulate here. Okay, so, this probability, I mean this aspect of one type of spin going through a ferromagnetic layer is called spin polarization. Okay. So, it is expressed by this beta. So, basically the difference in the resistivity, or you can express in terms of the density of states. Okay, so, in ferromagnetic materials you have different density of states for spin up and spin down electrons, right. So, the difference in the density of states of spin up electron minus the density of states of spin down electron divided by the sum is called spin polarization. So, what it means is that if you send electrons, majority of the spin up electrons will go through, and a fraction of this spin up also will bounce back. But if out of the several spin down electrons that you send, many of them will return back, only few may go through. Okay. So, the probability of spin up electron going through a ferromagnetic layer with a magnetization like this is higher. The probability of this one going to the other side is lower. Okay. Majority of this will come back. So, that is called spin polarization. The second concept that you need to know is the angular momentum transfer. Okay, so in this case, let us say we send electrons from bottom layer to the top layer. So, this fixed magnetization layer will send this type of spins to the other side. Okay. So, the majority spins will go, and the spins which have magnetic moment in the opposite direction to this, they will come back, okay, or they will accumulate here. Only the spin up electrons will go through. So, I will play the video again. Did you watch the video in the first round? Okay, let me try again. Yeah, yeah. Okay, let me split into 2 slides. I think that's better. Okay, so initially the 2 layers are in anti-parallel direction. Initially the 2 layers have anti-parallel magnetization. But when we send electrons through this side, actually we are sending current this way. So, conventionally the current direction is opposite to the flow of electrons. So, if current is the conventional current is in this direction, electrons are flowing from this direction. So, we are sending spin ups and spin down electrons through this layer. So, when these electrons come to this part, so we know that this will spin polarize. That means, the majority of the spin up will go here. So, a lot of spin up electrons will go, spin down will return back. Okay. So, when these spin up electrons go, they will exert a torque on this layer, okay, just like the rotating wheel passed a torque to the person who was sitting on the stool, right. So, in a similar sense, the angular momentum of the electron spin will exert a torque on the magnetization M. Okay, so that is what you saw in the video. Let us see whether it can play again. Okay, anyway, that is what happened. Because of that, this magnetization changed from this direction to parallel. So, we switched from anti-parallel direction to parallel direction. Okay, so, this was possible because of the 2 concepts that we learnt. First concept is polarization, That means, when we send electrons through certain ferromagnetic layer, the electrons with the magnetic moment opposite to the magnetization, they will get scattered back, and the electrons with the magnetic moment parallel to the magnetization will flow across. That is the polarization concept. Secondly, the electrons which go to the other side of the free layer, they will exert a torque. So, there will be angular momentum transfer happening. As a result, the magnetization of the ferromagnetic layer on the other side of the reference layer will switch. Okay. So, this is basically the spin transfer torque switching. Okay. So, here I am explaining the same thing again. Now, no video. So, we have electrons. So, this magnetization is polarizing, which means the electrons with the magnetic moment parallel to this are going to the other side. We are learning about anti-parallel to parallel switching. So, initially these two magnetization are anti-parallel. So, if this is pointing up, the other one is pointing down. Okay. So, when these electrons go to the other side, they will transfer torque to the magnetization here. As a result, finally, this will switch. Okay. So, we will go from anti-parallel state to parallel state. So, the MRAM guys always use the abbreviation. So, they will say AP to P switching. Okay. AP stands for anti-parallel, P is for parallel magnetization. Suppose we want to switch from parallel to anti-parallel, what do we do? What can we do? Yeah, we reverse the direction. Okay. So, instead of sending electrons from this side, we send electrons from the other side. Okay. Now, the initial configuration is both the magnetization are parallel. Okay. So, now we send electron from this side. So, we have spin up electrons, spin down electrons. So, this layer has magnetization pointing in this direction, and this layer also has magnetization pointing in this direction. So, when you send these two, the spin up electron will go through, it will do nothing, but the spin down electrons cannot go through this layer. Okay. You know that it will be scattered, right. So, these scattered electrons will accumulate here. So, you will have an accumulation of spin down electrons, and they will switch the magnetization. So, when you have a lot of spin down electrons, they will exert a torque on the magnetization of this layer and switch it to be anti-parallel. So, this is how we achieve parallel to anti-parallel configuration.
In the first kind of switching, switching is because of electrons which get passed through. In this kind, it is because of electrons which get accumulated.
Yeah, accumulated. Yes. Yeah.
And but they are minority, right? Lot of current may need for this.
Yeah. So usually AP to P needs less current compared to parallel to anti-parallel, slightly more current. Yes. Initially, free layer will be anti-parallel. I mean, we do not know whether free layer is anti-parallel or parallel. So, it is just that if you want to write 0, you send current in one direction. If you want to write 1, you send current in the opposite direction. Okay. So, in a memory you do not know whether the memory is in 0 or 1, you do not know whether it is parallel or anti-parallel. So, just depending on whether you want to write 1 or 0, you send the current in one direction or the other direction, that is all. Okay. So, this spin transfer torque concept is again coming from magnetic recording. Okay. So, I told you magnetic recording is the father of all MRAM related technology, okay, except SOT that we will learn later. So, when people studied the read sensors, right. So, in read sensor, for example, GMR or TMR sensors, we have one reference layer and one free layer. We send current through the layers to read the resistance state, right. So, if the recording media is making them parallel, we will have low resistance. If the recording media magnetic field is making them anti-parallel, we will have high resistance. Okay. So, we are sending a current which is called sensing current to read the bits in hard disk technology. Okay. So, when people were studying this one, they realized that the current you send through the sensors is affecting the magnetization. Okay. So, they noticed that the current you send through the sensors for reading information is affecting the magnetization state. Okay. So, at that time two scientists, one is called Slonzewski, I may be wrong in spelling, and another scientist called Berger. So, these two predicted that, I mean theoretically they predicted that if you send current through something like this MTJ or something like that, the current you send is causing spin transfer torque. Okay. So, this was a theoretical prediction in 1996 based on magnetic recording principles. Okay. So, when you are talking about magnetic recording principle, you do not want the magnetization of the sensor layers to be affected by the current that you flow. Okay. So, this magnetization should be parallel or anti-parallel only because of the magnetic field that comes from the recording medium. It should be independent of the sensing current. Okay. So, this was considered like a negative effect, unwanted effect. So, in the case of read sensors of hard disk drive, this current affecting the magnetization states is the unwanted effect. Okay. So, it was proposed in 1996. Then somewhere a few years later, people realized that we can use this to write information. Okay. So, people thought that okay, we have this spin transfer torque effect, why do not we use this to switch MRAM. Okay. So, with that objective, people have started studying whether we can switch the magnetization of MRAM by sending current through the device. Okay. So, this is one of the earliest studies of spin transfer torque switching. So, around 5 years after the theoretical prediction, people showed that you can switch magnetization of MRAM layers by sending current through them. Okay. So, in this case this is a GMR. So, you have a copper spacer CPP GMR. Okay. So, you are sending current perpendicular to the plane. This is a CPP GMR device. So, you have two ferromagnetic layers cobalt separated by a copper spacer. So, this is a CPP GMR, you are sending current through this way. Okay. So, if you look at this graph, it does not have any magnetic field. Okay. there is no magnetic field, sorry, this is the there is no magnetic field, and you only see the current in the x axis and resistance here. Okay, let us say we start from here. We have certain current and we go towards the other direction. Then suddenly you see a change in the resistance. Okay, that is because the current in this particular direction has changed them from parallel state to anti-parallel state. So, we have low resistance when the magnetization are parallel, right. We have high resistance when the magnetization are anti-parallel. Okay, so, they notice that at certain value of current, this device switches from parallel to anti-parallel. So, now you have high resistance, because now they are in the anti-parallel state. Now, you go along this line, change change the current direction. So, now negative to positive, at certain value you see that it has switched from anti-parallel to parallel configuration. Okay. So, here they did not apply any magnetic field, only by changing the current amplitude and the current direction they can go from parallel state to anti-parallel state. So, this experiment proved that we can switch the magnetization states by sending current through the device and by using spin transfer torque mechanism. So, this graph also answers your question, right. So, when you go from parallel to anti-parallel, we need more current. Okay. When you go from anti-parallel to parallel, you have less current. Okay. So, this video summarizes everything that we discussed. So, initially we have anti-parallel state, we are sending electrons from this side. So, the majority electrons go to the other side and switch the magnetization from anti-parallel to parallel. Now, we are switching from parallel to anti-parallel by the spin accumulation here. Okay, so, this basically the spin transfer torque switching mechanism.
So, that accumulated electrons, then where it goes in last, like when the switching is done?
Yeah, I mean, I haven't thought about this one, but this is a metal. I am not sure, maybe another time I will tell you. Okay, so, now the theory part, you do not need to worry too much if you do not understand. Let us say you have a magnetization, okay, shown by this red color arrow, and you apply some magnetic field. Okay, so, this is what we normally do, right. We take magnetic material with certain magnetization. When we do hysteresis loop, this is what we do. We have magnetization in one particular direction, we apply certain magnetic field, and what this magnetic field does to the magnetization at smaller time scales. Okay. We are now talking about time scales in the order of picoseconds, what happens. Okay. So, if magnetization is pointing in this direction and you apply magnetic field along this direction and there is some angle. Okay. So, this magnetic field will cause a field like torque. So, what happens, this magnetization will precess around this magnetic field. Okay. So, the magnetization will go around like this. So, if magnetic field is like this, magnetization is like this, it will go around like this, precise like this. Okay, so, the precision path is shown here. So, that term is called field like torque, it is given by this formula. So, it is in the direction perpendicular to both the magnetic field as well as the magnetization. That is one thing. Secondly, this precession cannot happen forever. Okay. So, in systems when this kind of precession happens, some energy transfer happens. So, finally, the magnetization precession will be damped, okay, which means the precession will slowly die down, and finally, this magnetization will point along the direction of this magnetic field. Okay, so, this damping is given by this formula. So, is a cross product of m and dm over dt. So, m is along this direction and dm dt is along this direction. So, basically this damping what it does is it brings the magnetization parallel to H. Okay. So, the damping torque moves the magnetization parallel to H. How many of you here do LRG simulation? 1, 2. Okay. So, if you are doing mu max simulation, mu max 3 or WUMF, so basically you are using LRG equation. So, in LRG equation, the Landau-Lifshitz part LL is by two scientists, Landau and Lifshitz. They came up with this term that if you have a magnetic field at certain angle with respect to magnetization, magnetization will precess. That is the term introduced by Landau and Lifshitz, and Gilbert is the one who introduced this damping part. Okay. So, after Gilbert's introduced the damping part, so we know that this magnetization will finally settle along the direction of magnetic field. So, these things happen, and you should know that torque is the equivalent version of force in rotational motion.
So, while you were writing over there, H effective.
Pardon?
H effective.
H effective is some magnetic field. Okay. For example, let us say you have only one particle, okay, only one particle with the magnetization like this, and you apply a magnetic field. Okay. So, this is applied field. You can say that this applied field will do the same thing as what is shown here, but in a system there may be many other sources of a magnetic field. Okay. So, it need not come only from the magnetic field that you apply. So, there can be say magnetic field from the neighboring atomic moments and so on. So, this effective field is the field seen by this particular magnetization. So, it can be coming from any other source. So, when we do LLG equation based simulation, so this H effective can be coming from the external field we apply. So, we usually call this at H Zeeman. Okay, then this H can come from the anisotropy. There are so many sources of this H effective. So, this H effective will include all the terms, different terms that a particular magnetization sees inside the system. Okay, so, now we go on to the STT. So, we are sending electrons from left to right. Okay, so, this is the free layer that we want to switch. Okay, so, this is the reference layer or polarizing layer. Okay. So, when you send electrons through this layer, so we have learnt about polarization. So, the electrons which are in the same direction as the magnetism go through to the other side. Okay. So, when these electrons go to the other side, this free layer magnetism will experience one effective field given by this term, and it will also experience a torque given by this formula. Okay. So, normally what you do when you do the simulation of hysteresis loop or something, we normally only do two terms. Okay. So, if you are simulating a hysteresis loop M versus H, then these two terms are enough. Okay. But when you are simulating spin transfer torque, for example, so in that case you have to include these few terms, okay, coming from the transfer of these electrons to the other side and the torque these spins exert on the free layer and so on. Okay. So, these are the terms that people use in the energy equation to study the spin transfer torque. Okay. The most important concept that you should remember here is that the projection of this particular M perpendicular to the free layer is the one that gives rise to the torque. Okay. Let us say this is your M pin. Okay. So, it can be resolved into two components, right. One is the blue and another one is along this one. Okay. So, only this component which is perpendicular to the magnetism will cause torque. Okay. So, when many electrons go to the other side, this component keeps changing, I mean this component keeps exerting a torque on the magnetism. So, these two should be perpendicular. Okay. Only the perpendicular component causes the torque. Okay. So, in a toy quantum mechanical model, what happens is that when a spin of this type goes to the other side, it will make the magnetism tilted by a certain angle and it will bounce back like this. So, angular momentum transfer is shown in this picture. Okay. So, we call the reference layer with many names, right. I told you we can use the word fixed layer, hard layer, reference layer and so on. We can, some people also use the word polarization layer for the same reference layer. Okay. So, what we expect from the reference layer of a STT MRAM is that the reference layer should have as high polarization as much possible. Okay. So, if the polarization of that material is high, then we can achieve switching better. So, that is one criteria. The second criteria is that this reference layer should be extremely stable. That means, the current you send through the STT-MRAM should switch only the free layer. Okay. So, that current should not switch the magnetism of this layer. So, the reference layer should be always pointing in one direction. So, that is second criteria. Either we can choose a material with a large coercivity or we can pin the reference layer using exchange bias. So, that is second point. And when it comes to the reading part, the TMR depends on the crystallographic texture of the magnesium oxide. So, this one we will do day after tomorrow. So, day after tomorrow you will learn that this magnesium oxide has to be in 001 texture. So, that will give rise to high TMR. So, when we design reference layer, you should design in such a way that the reference layer does not affect this 001 texture of magnesium oxide. Okay. So, that is the third condition. So, it should not deteriorate the 001 texture of magnesium oxide. Okay. So, when you write I mean when you switch magnetization from one direction to the other direction, it does not flip like this. Okay. It goes through a precession mechanism. So, we learned that the different torques will make the magnetization to switch in certain path. Okay. So, if you apply current for a short time, let us say you apply certain pulse width. Okay. So, you apply certain current pulse with a certain pulse width. So, if this current amplitude is lower than what is required, what happens is that maybe your spin will precess for some time, then finally settle in the same direction. So, switching will not happen. Only when this amplitude meets the critical current, we can achieve reversal. Okay, so, I will show a few animation. So, here the pulse you apply, the current is not below the critical current. So, you see that the magnetization just oscillated, then it did not switch. So, if the current is too high, if it is more than the critical current, then it can switch faster. Okay. So, even though your pulse width is so large, you can switch much before your pulse ends. Okay. So, what it means is that during all this time you are wasting energy. Okay. So, people normally choose the right, I mean the critical current for that pulse width. Okay. So, if you choose the right current for the right pulse width, then you can achieve effective switching. Okay, let us do some questions. You need to log in again. So, let us go to the questions. Okay, regarding your question, what will the accumulated spins do, right? So, we are talking about metallic layers. So, in metallic layers the electric field cannot exist, right. So, the accumulated spins should go back. They I mean spins cannot accumulate and they will go back, right.
To the same wire.
Yeah, they will go back to the other side. Yes. Accumulation of electron will give rise to electric field, so it cannot happen. But in semiconductor, I don't know. Your case, I don't know. Okay, so let's look at the result. Okay, many of you are wrong. The reference layer is doing two things, right. So, let us say you go from parallel to anti-parallel. So, you are sending electrons this way. Okay. So, the spin up electrons go out this way, but the spin down electrons get reflected back, right. Spin down electrons accumulate here and they are the one causing the reversal of this magnetization from parallel to anti-parallel. Okay. So, in this geometry the reference layer reflect electrons into the free layer. On the other hand, if you go from anti-parallel to parallel, you are sending electrons this way. So, spin polarized electrons go to the other side and reverse this from anti-parallel to parallel. Okay. So, in that case you are sending spin polarized electrons into the free layer. So, in one case you are sending spin polarized electrons into the free layer, in the other case you are reflecting spin polarized electrons into the free layer. So, C is the correct answer. So, all of the above is the correct answer. It is doing both. Next one. Parallel to anti-parallel, we send do you know why many of you are wrong? Yeah. So, I am just saying current. Okay. So, conventionally current and the electron flow are in opposite direction. Okay, next one. Oh, here again. Here I am talking about electrons, right. So, to switch from anti-parallel to parallel, okay, let us go back. To switch from anti-parallel to parallel, we are sending electrons this way. Okay. So, they get spin polarized. So, the spin up electrons come to the other side and switch the magnetization. Okay. So, the electrons are sent from reference layer to the free layer. So, this is the correct answer. Okay, so, now we move on to the next topic. So, currently the STT MRAM is already a product, as I told you. People are using STT MRAM as a e-flash memory. So, STT MRAM can be operated at around 10 power minus 12 ampere per square. So, the current density that you require to operate STT MRAM is typically around 10 power 12 ampere per square meter. Okay. So, people are looking at, okay, this is one thing. Secondly, STT MRAM can operate at speeds of in a time scale of 10 nanoseconds. So, typically like say 100 megahertz kind of thing. Okay, so, that is the speed in which STT MRAMs can operate. So, people are thinking of how can you increase the speed, whether you can go from 10 nanoseconds to 1 nanosecond kind of time scale, and whether you can reduce this current density from 10 power 12 to say 10 power 11 or 10 power 10 ampere per square meter. So, these are the questions the researchers have. So, we want to make faster devices, we want to make devices that consume less power. Okay. So, in that aspect people are working on another type of MRAM called spin orbit torque MRAM, SOT MRAM, which stands for spin orbit torque. Okay. So, this spin orbit torque MRAM operates on this physics called spin orbit coupling. Okay. So, spin orbit coupling is the interaction between the spin angular momentum of an electron and the magnetic field generated by its motion around the nucleus. Okay. So, that is too wordy. So, let us look at what happens. So, you have certain nucleus. So, nucleus has protons. So, it has a positive charge and the electrons are orbiting around. Okay. So, this is from proton's point of view. So, proton is looking at electron going around. Okay. But if you look from the electron's perspective, it is like the proton is going around. Okay. So, if you look from the electron's perspective, a charge is going round. Okay. So, we learnt that in solenoid, right, in solenoid you are sending current through a loop. Okay. So, current through a loop produces magnetic field, right. So, we learnt before. So, in this case this is a charge going around. So, that is like a current flowing around. So, this electron will see a magnetic field. Okay. So, when electron goes around a nucleus, basically the electron will see a magnetic field, and that magnetic field is given by this formula. Okay. So, it depends on the charge of proton and the number of protons inside the nucleus. Okay. So, this is the magnetic field. So, the magnetic field and the spin will interact. So, there will be a shift in the energy of electron. Okay. So, spin up electrons will have, so spin up and spin down electron will have different kind of energies. Okay. So, this is basically the spin orbit interaction, and we can observe the spin orbit interaction by observing the torque exhibited by the spin orbit coupling effects. Okay. So, when people talk about spin orbit torque, we are talking about some heavy metals. Okay. So, if you remember the formula I showed you, there was a G, right. So, if the G is large, then the magnetic field is supposed to be large. Okay. So, in heavy metals have a large number of protons, right. So, in heavy metals G is large. So, this B is going to be large, then the spin orbit coupling is going to be large. So, when we talk about spin orbit torque MRAM, we always deal with heavy metals like tungsten, platinum, tantalum, all these are some examples of heavy metal layers in which we have observed spin orbit torque. Okay. So, because of the spin orbit interaction, so I told you that it is spin dot B, right. So, one type of spin will have one energy, another type of spin will have another energy. Okay. So, because of that, when you send a current through a heavy metal layer, one type of electron will go to one side, another type of electron will go to the other side. Okay. So, this is called spin Hall effect. Okay. So, normally what do you say when you say Hall effect? So, what we do, we take a semiconductor, for example, we apply a magnetic field. So, because of this magnetic field, electrons go to one side, holes go to other side. So, if you measure the voltage, you will see some voltage, right. So, in the case of normal Hall effect, you will see a voltage because electrons go to one side, holes go to another side because of the magnetic field that you apply. Okay. So, when we talk about spin Hall effect, we do not need to apply any magnetic field, but because of the spin orbit coupling, there is already the S dot B interaction. Because of that, one type of electron, say for example, spin down electron goes to this side, spin up electron goes to the other side. Okay. So, this is called spin Hall effect, and you can use this effect to switch the magnetization and make MRAM devices. Okay. So, this spin Hall effect was proven experimentally somewhere in 2012. Okay. So, in this case they deposit tantalum. Do they show the detail here? Okay, I think this is tantalum, even though the slide does not show. So, they have a heavy metal layer like tantalum on at the bottom, then they have a ferromagnetic layer on top. Okay. So, at first they measure the anomalous Hall effect. So, anomalous Hall effect is another form of Hall effect, which is which can give rise to the information about magnetization. Okay. So, if the resistivity shows you this kind of hysteresis loop, so it is like measuring magnetization as a function of external magnetic field. Okay. So, anomalous Hall effect is quite often used to measure hysteresis loops electrically. Okay. So, electrically anomalous Hall effect can give rise to loops like this. So, in this study they are measuring the magnetic properties of this ferromagnetic layer using anomalous Hall effect. So, at first they demonstrate that this magnetic material shows hysteresis loop like this. Okay. So, in the next slide what they do is they send a current through the tantalum layer. Okay. So, here the external, there is a little bit of external magnetic field, okay, but this is fixed, this one is constant. Okay. It is not changing when they do the experiment. Okay. So, what they change is the current they send through the tantalum layer. Okay. So, they send current through the tantalum layer, and because of this current they see switching. Okay. So, magnetization is initially in this direction. So, at some current it switches to another, say let us say magnetization is like this or like this. Okay. Then again when they sweep the current, they see the magnetization going from that direction to this direction. Okay. So, they can see the magnetization switching just by sending current through the tantalum layer. Okay. So, what happens is when they send current, let us say now this is a cross sectional view. So, this is a tantalum for example. When you send the current through the tantalum layer, so one type of spin accumulates here, another type of spin goes into the opposite direction, then you can see down spin is here, up spin is here. Okay. So, they typically follow this circular relation. So, spins go all over to the different edges of the heavy metal layer. So, when this type of spin goes up, it can switch the magnetization from pointing left to right. Okay. So, here you notice that there is no special polarizing layer. Okay. in the case of STT MRAM, you had a ferromagnetic layer, that ferromagnetic layer polarized your spins, and because of that polarized electrons you were switching. But in the case of spin Hall effect, you are just using a heavy metal layer like tantalum or tungsten, and using the spin Hall effect you accumulate certain type of spin which helps to switch the magnetization. Okay. So, this is called spin Hall effect. Yeah.
In the previous slide,
Mm-hmm.
is that negative resistance?
Negative resistance. So, what it means is they apply some current, they measure the voltage, and for calculating the resistance they will just divide this voltage by so, okay, let me tell you what they do exactly. So, a Hall bar looks like this. Okay. So, when we do anomalous Hall effect, so the anomalous Hall effect, the anomalous Hall bar will look like this. So, we send current through this side. Okay. So, we have current going through this one, and we measure the voltage across this. Okay. Across these two sides we are measuring the voltage. So, this voltage depends on the spin accumulation, say let us say one type of spin is here, another type of spin is here. So, because of this difference in the number you will have some voltage. Okay. So, when they plot resistance, they are dividing this voltage by this current. Okay. So, it is not like so when you measure the resistance of this wire, for example, let us say you have a wire, you want to measure the resistance of this wire, we use the term R x x. So, we have two current leads, then two voltage leads, then you divide this voltage by current to get R x x, right. But in this case we are measuring R x y. That means current is flowing in the x direction, you are measuring the voltage in the y direction. So, you are dividing this voltage by current. Okay. So, this voltage will depend on whether the magnetization is pointing into the board or pointing towards you. Okay. So, this voltage will be like positive or negative irrespective of this current direction. Okay. So, because of that you will see sometimes positive, some another case negative. Okay, so people use some terms like spin Hall angle or spin, torque, efficiency to determine how efficiently we can switch information, I mean switch the magnetism using the spin Hall effect. So, spin Hall angle is basically defined as the ratio of the spin current by charge current. Let us say you send certain charges here and how much of that results into spin current, and this ratio is called spin Hall angle. So, sometimes people also use the word spin torque efficiency. Okay. So, if you want to make spin orbit torque MRAM, okay, now let us see how we can use the spin orbit torque to switch and make MRAM devices. Okay. So, a spin orbit torque MRAM may look like this. So, you have two transistors, they provide current. So, this current flows through the heavy metal layer, and because of the spin orbit torque, certain type of spin goes into this free layer. Okay, so, this is an MTJ, you have free layer magnesium oxide reference layer, and you are switching this free layer magnetization by sending current through the heavy metal layer. Okay, so, this heavy metal layer sends certain spin to this layer, and because of that you can switch the magnetization. Okay. So, this is the design of SOT MRAM. So, there are some benefits and problems of this particular design. Okay. First, let us look at the benefit. For that, let me go back to the empty screen. So, in the case of STT MRAM, right, STT MRAM, you have a magnesium oxide layer, then you have a reference layer, and you have a free layer. Then you are sending current either this way or in the opposite direction to switch parallel or anti-parallel. Okay. So, here the read and write path are the same. So, if you want to write information, you send current through this path. If you want to read, whether it is 0 or 1, again you are sending current through the same path. Okay. So, the read and the write lines are the same.
Don't there is the risk of flipping a bit while reading?
Okay. So, what we do when we read, we send a smaller current. Okay. So, we do not want to switch the bit when we read information. So, for this reason the write current is more than the read current. Okay. So, the advantage of the STT MRAM is you just need one transistor. Okay. One transistor is enough. So, it can supply current to write information, and it can supply current to read the information. So, basically you need only two terminals. Okay. So, let us use this word, only you need two terminals, okay, terminal 1, terminal 2. With just two terminals you can read and write information. Okay. So, it is less complex. But the problem with this design is, I told you that the writing current is larger than the read current. So, the writing current goes through this device. So, let us say we write billions of bits. So, every time you write information, so the device will get heated a bit, right. So, there is a Joule heating. So, if the device has a resistance R and this is your write current. So, there is some Joule heating produced. So, when there is some heating, there will be some diffusion of atoms. Okay. So, maybe some atoms of magnesium will go, or sometimes the oxygen atoms may go somewhere. Okay. So, when you do repeated writing operations, this tunnel barrier, the magnesium oxide may break down. Okay. So, in the MRAM industry, they use this terminology TBBD, which means tunnel barrier breakdown. So, after many operations of writing, because the write current is quite large, it can damage the magnesium oxide layer. Okay. The tunnel barrier may break down. So, this is the problem of STT-MRAM technology. But when you go to the SOT-MRAM technology, your MRAM look like this. So, we have 3 layer at the bottom, reference layer at the top, magnesium oxide is here, this is your heavy metal. So, when you are writing, you are sending the current through the heavy metal. Okay. So, this is the writing path. When you are reading, you are sending. Let me use another color. Okay. So, for reading you are using another path, for writing you are using different path. So, the writing current is larger than read current, right. But the larger current is now not going through this device. Okay. So, it is going through the heavy metal. So, heavy metals are usually reasonably good conductors. So, they pass the current relatively without much problem, and this tunnel barrier does not break. Okay. So, this is the advantage side of SOT-MRAM. So, you do not have the tunnel barrier breakdown. So, you do not have this problem in SOT-MRAM. Secondly, SOT-MRAMs can be operated at 10 power 11 ampere per square meter. So, the current density is typically 10 times lower. So, if current can be 10 times lower, power can be like 100 times lower. Okay, so, these are some of the advantages of spin orbit torque MRAM. Okay, so, current passes through the barrier only during the reading. So, tunnel barrier does not break down. So, these devices have a longer lifetime. Okay, but the disadvantage is now you need 3 terminals. Okay, so, you need 2 terminals for writing operation, another 2 terminal for reading operation. Okay, so, 3 terminals occupy more space and the device is a bit more complex. Okay, so, there are disadvantages and advantages of SOT-MRAM. And I will show some more slides to show some other advantages. Okay, so this slide summarizes everything about STT MRAM and SOT MRAM. So, in the case of STT MRAM, usually see the switching speed is around 10 nanosecond. If you go lower than 10 nanosecond, you need more and more current. Okay. So, this is like energy, you need more energy to switch, but if you operate around 10 nanoseconds, you do not need to spend much energy. So, this is a feature of STT MRAM. On the other hand, SOT MRAM, you can operate at 1 nanosecond, okay, without much additional energy. So, SOT MRAM help to achieve high speed. So, because of this reason, people are thinking of using SOT MRAM as a replacement for SRAM. SRAMs also operate at high speed around 1 nanosecond. So, people are thinking of replacing SRAM with SOT MRAM. So, if you are not worried about the speed, you can use STT, but applications like SRAM where your speed is very important, you can use SOT. Okay, so people have, I mean, this one result I wanted to show. People have studied SOT MRAM in different configuration. So, these two are like in plane MRAM, right, where magnetization is parallel to the disk surface. Then this one is a perpendicular. So, here again we have two different type in plane. One is called type X, where the magnetization is in the same direction as current. Type Y means magnetization is perpendicular to the direction of current. Okay. So, let us say this is a heavy metal layer. When you send the current in this direction, let us say x direction, you are sending current. So, that will produce spin polarization along the y direction. Okay. So, the spins pointing along the y direction. Okay. So, let me zoom this one. So, this is x, this is y, z means perpendicular. So, when you send current in the x direction, the spins will be pointing in the plus y or minus y direction depending on your current direction and the material property. Okay, the spin that goes up towards the ferromagnetic layer is pointing in that direction. Okay. So, if magnetization is pointing anti-parallel to this spin, so this spin will exert torque on this one, then switch. Okay, that is quite normal, we learned that before. But if you want to make these spins to switch either perpendicular magnetization or magnetization at an angle of 90 degree with respect to this spin, usually we need to apply certain magnetic field. Okay. So, we call that symmetry breaking field. Okay, so, you do not need to worry too much about all these things. basically you can make MRAM in 3 geometries, but I mean this is only physics study. We are not going to use these 2 in products, because we are going to use perpendicular MRAM. So, basically you need to apply certain field Hx. So, you need to apply a magnetic field along the direction of your current to break certain symmetry. Okay. So, when we talk about breaking symmetry, what it means is when you send this spins in the y direction, we usually use the symbol sigma y. So, this sigma y spins are going to the ferromagnetic layer. So, this sigma y spins can switch the magnetization from perpendicular, I mean pointing up to pointing down, but this is not stable. So, again these spins can act on this magnetization and they can make it perpendicular. So, these two are equally almost same energy. So, they will just go up and down. You cannot keep the spin in one particular direction. So, to break the symmetry, we usually use a magnetic field in the x direction. Okay. So, out of so many things as I show in this picture, only this is relevant for application. We will be using perpendicular MRAM. So, in perpendicular MRAM, we send a current in one particular direction, and we need a magnetic field along the current direction. But people are trying to overcome that problem. So, when you make MRAM and sell it to people, you want to operate without that Hx field. Okay. So, you just only want to send current through the device to switch. Okay. You do not want this one. So, there is lot of research going on how to achieve field free switching. Okay. That means, without this Hx can you switch the magnetization. So, for that people are trying to use some antiferromagnetic layer below the perpendicular magnetic layer, or I mean there are many other topics. Even in my group we are doing a lot of research on how to achieve field free switching, and you do not need to worry about all these things. Okay. As a summary, we can switch the magnetization of the free layer of MRAM. So, switching free layer magnetization of MRAM is called writing. Okay. So, this writing can be achieved using magnetic field. So, you can send current through 2 orthogonal wires and achieve switching. That is what we learned first, and this technique is extinct. Nobody uses this one. The second candidate is using the spin transfer torque principle. So, you can send current through the device, you will generate some spin torque, and you can use this to switch magnetization. We did not discuss this today, and we can also use spin orbit coupling. So, use spin orbit torque to generate spins. So, these spins are purely coming from non-magnetic materials, okay, like heavy metals, iron, platinum, sorry, not iron, platinum, tungsten, tantalum. These kind of materials are used for generating spins into the ferromagnetic layer, and we can switch magnetization. So, we learned these 3 topics today. Okay. Any questions? Yeah.
What is the principle behind removing this HX?
Using the Hx, is it?
No, like
Hmm?
in this slide we are using antiferromagnetism. So
Okay.
why would
So, how the antiferromagnetic material will overcome, I mean help in the Hx? Okay. let us say this is a magnetic material with a perpendicular magnetization. So, in the absence, let us say you only have heavy metal layer, the magnetization will be like this. Okay. Now, let us say you deposit this ferromagnetic layer on top of antiferromagnetic layer. So, this antiferromagnetic material has spins like this. So, there is a horizontal component of magnetization at this edge compared to the other edge. Okay. So, the magnetization, if you go from top to bottom, maybe they are something like this. So, you have some canting of spins in this region because of the interaction of antiferromagnetic material with this part of the ferromagnetic layer. So, you have some canted spin. Okay, so, you can imagine that this is like having two components. Okay. So, this component helps in getting rid of the HX.
This spin polarization will be possible in AFM.
Yeah, spin polarization is possible. I mean, yeah, in this case they have shown iridium manganese as the heavy metal layer. Yeah, I mean they have demonstrated this, so it works.
Like, one question. Can you replace this heavy metal with some composition which have high spin Hall effect coefficient?
So, you are saying whether we can, so you are talking about doping or?
No, like the people who are trying to, like working on layered materials which has high spin Hall effect signals. So that can replace the heavy metal in this architecture? Or?
Okay, there are a lot of research on which is the best material to have spin Hall effect. So, so people normally use like platinum, tungsten or tantalum. These are standard materials when you just want to focus on other aspects, okay, where spin Hall effect is one mechanism that you use. Okay. Then if you want to enhance the spin Hall effect, there are lot of research directions. So, some people use study doping, say platinum with tantalum or tantalum with copper. So, people try doping, that is another way. Then people are also looking at what do you call the while semi metals, topological insulators. So, a lot of materials are being studied to see whether we can achieve high spin torque efficiency. So, while semi metal, topological insulators all are being studied. Yeah. So, that is one aspect. So, in my group we are also looking at another phenomenon called the orbital Hall effect. Okay, so, let us say you have some material. So, in this case we are looking at light metals like chromium, those kind of light metals. So, we send current. So, here one type of one type of orbital electrons go one side, another type of orbital electrons go to another side. So, we have orbital Hall effect, but orbital Hall effect cannot be coupled to magnetization. Okay. So, orbital Hall and orbital part of electron and magnetization cannot be coupled. So, what we do, we exploit the LS coupling. So, we convert orbital torque into spin torque through some mechanism. For example, let us say you have chromium is the orbital Hall layer. So, there is a orbital Hall effect. We convert that into spin Hall effect by having let us say thin layer of platinum. So, we have L s, then we generate spins that go up to the ferromagnetic layer. So, S can be coupled to M. Yes. Then with this L s conversion we can switch the magnetization. So, there are a lot of research going on. So, whether you can investigate on doping materials or you can investigate exotic materials like topological insulator, wild semi-metals, or in another direction you can look for new effects like orbital Hall effect to switch. So, lots of research is going on. Slide 36 elaborate again about resistance of parallel and okay, slide 36 is one of the earliest demonstration of spin transfer torque switching. So, in this case they are trying to switch the magnetization of the ferromagnetic layers with no magnetic field. Okay. So, normally when we do hysteresis loop we switch magnetization with a magnetic field. So, in this case there is no magnetic field at all. Okay. So, they send the current through this device. Okay. So, either they send current downwards or they say they can send current upwards. Okay. So, we can call one of them positive, another as negative. So, if we start from this point, so you can see that there are two states, one is this state, another is this state. Your y axis is the resistance. Okay. This is resistance. So, this is basically high resistance, this is low resistance. Let me use a different color. Okay, the green line is low resistance state, red line is high resistance state. So, we know that the resistance will be low when the two layers are parallel to each other. And we also know that the resistance is high when the two layers are anti-parallel to each other. So, this is a GMR device. So, this is a ferromagnetic layer, copper spacer, ferromagnetic layer. So, this is a GMR device. Okay, so, let us say we start from point A in this picture and go towards negative current. So, we follow the green line path. Okay. So, starting point we are in the parallel state. So, when we go towards certain current say minus somewhere here, we can see that the resistance has changed. It has gone to a high value, which means at this particular current we have achieved anti-parallel configuration, which means the magnetization of the one of the layer has switched from being parallel to anti-parallel state. Okay, so, we come to the point B, we achieve switching. Then again when you go from point C towards let us say point D. Okay, when you go through C, B, D, you are in the state of high resistance, then at some point D you are switching to a low resistance state. Okay, so this is what I demonstrated. Okay, got it. Thank you. Any other question?
Yes, sir.
Yeah.
So in SOT, different types of geometry, type Y and type X are in-plane geometry.
Yeah, yeah.
Why they are not considered? Because type Y already has a possibility of field-free switching.
Yeah. Type Y is considered for some specific applications, like that particular group in Tohoku University. They are using type Y for some form of computing. Okay. So, for that particular application type Y is useful, but when we are talking about MRAM later we are going to learn about storing information tomorrow. So, at that time you will realize that the perpendicular MRAM is more useful than in plane MRAM. Okay. So, it is very similar to the longitudinal magnetic recording and perpendicular magnetic recording. So, there are many benefits when you store information magnetization in the perpendicular direction. Okay, any other question? Okay, if not, we stop here. So, tomorrow we will learn about how do we store information. So, stay here until Professor Datta comes. So, we will take group picture.
In this orbital orbital horizon, why did we use chromium? It's already in 3D and we less contribution.
I mean, you can use